My name is Edward Wang, and this work was done together with my supervisor, Professor Björn Gabrecht at TUM. So to start, let's look at a bit of motivation. As we all know, there are three very important shortcomings of the standard model, namely, it cannot explain neutrino masses, it cannot explain the baryon asymmetry of the universe that we see today, and it cannot account for the dark matter that we observe. Now, the goal of this project is to try to address these three issues with a single extension to the standard model. Now, let's look at what a specific model is. As we have seen from Joachim's lectures, we know from neutrino oscillations that at least two neutrinos are massive. And in order to produce these two neutrino mass states, one usually adds two Majorana-fermions that couple to a Higgs and couple to the standard model neutrinos. Now, Ibarra and Hen, they proposed a different kind of model, an alternative to this, in which they add a single Majorana fermion, but then they add two Higgs scalars, and together they will form together a dark sector. And from this, they show that you can also produce two massive neutrino states. Now, the interaction Lagrangian, they look like this. So this is precisely the Yukawa term that Joachim has shown to us. It's very similar to what Joachim has shown to us earlier today. And they produce the following vertices. So here we have a Yukawa interaction between the Majorana fermion, the standard model leptons, and to these new scalars that we call eta. And here we have scalar interactions between the etas and the standard model Higgs. Now, a very important thing about this model is that the neutrinos do not couple directly to the standard model Higgs, and the new scalars do not acquire a VAV, meaning that neutrinos do not get a mass at tree level, but only at loop level. And the loop level diagram looks like this. So here we have a Yukawa interaction, here a Yukawa interaction, and here we have a scalar interaction that couples the whole system then to the standard model Higgs at one loop level. The mass matrix that we obtain has this form. What is important to note about this is that here we have this product of the different couplings, and we have the masses of the particles in the propagators here in the denominator, meaning that if any of these couplings, or if all of the couplings are small, or if any of these masses are very large, we will automatically obtain small neutrino masses. What is also important to note is that, as I've mentioned before, we only have one Majorana fermion, but we have two doublets, scalar doublets, meaning that if we look at this mass matrix in more detail, we see that it has rank 2, meaning that, as I've said, we produce two massive neutrino states, which is what the minimal scenario in order to explain the oscillation data. Okay, now let's look a bit at baryogenesis. Any baryogenesis mechanism must fulfill the three so-called Sakharov conditions. The first one is departure from thermal equilibrium, because the asymmetry has to be produced dynamically, and in thermal equilibrium, essentially nothing changes, nothing evolves. The second thing is baryon number violation, which is clear. And the third one is CP violation. Now, departure from thermal equilibrium, this is in a way already accounted for by the expansion of the universe, because it expands and it's constantly driving the thermal bath out of equilibrium. Baryon number violation, we have theoretically, the spheruron processes are predicted already within the standard model, and they violate baryon number. So this is also already contained in the standard model. And now CP violation is given in our model by the Majorana fermion decay. And this is, as Joachim has also mentioned this morning, this is the scenario of leptogenesis, as we call it. So now let's look at these decays in a bit more detail. As you could see from the interaction Lagrangian, the Majorana fermion couples both to leptons and to anti-leptons, so it can decay, and it has both decay channels. And in principle, CP violation is possible if the Majorana fermion had a preferred decay channel into either leptons or into anti-leptons. And now the first attempt that we could do to try to see this would be to look at the tree level diagram. But what happens at tree level, we have a single diagram here. And if you take the CP transform of it, essentially what you're doing is taking the complex conjugate of the Yukawa coupling here, and meaning that you only get a single complex phase. But then to compute the rate, you have to square the amplitude, and this complex phase vanishes, meaning that you don't get any CP violation. So we would get the same rates for leptons and to anti-leptons. So we have to go one step further, namely at one loop level. At one loop level, what we get is this kind of diagram where we insert a lepton loop in the scalar propagator. And now, if we take the CP transform of it, we not only have to complex conjugate the Yukawa couplings, but we also have this internal loop, this internal propagators that we need to CP transform. And by doing this, in general, you will find a difference. You will also get a complex CP phase, which is in general different from the one that we had at tree level, meaning that once we add both diagrams together and we square them, we get an interference term from the different complex phases. And it's precisely this interference term that will be is responsible for ACP violation in these Majorana-Fermion decays. And if we compute these diagrams, what we find is that the decay symmetry is proportional to this term here. So here in the numerator, we have precisely what I've mentioned about the interplay between the different phases of the Yukawa couplings. And the denominator, we have this term stemming from this internal scalar propagator, which is the squared mass difference between the different scalars. And we'll see that this will become important because this allows for a resonant enhancement of the decay asymmetry in the case where the masses are very close to each other. Now let's assume that we have the following scenario where the Majorana-Fermion is much lighter than the two scalars. In the end, computing leptogenesis amounts to solving Boltzmann equations, as we have seen several times today. And in the end, what we find are kinetic equations of this form, where here we have the particle yields for the Majorana-Fermion, here the particle yields for the leptons. We take z, which is m divided by t as a form of time measure, a time variable. And so the first equation is telling us the evolution of the Majorana-Fermion. We have this collision term here that will try to equilibrate the Majorana-Fermions, and so try to bring them into thermal equilibrium. And in this process, because of the decay symmetry that we've seen before, this equilibration will be a source of lepton asymmetry, which is given by this term S. And we also have so-called washout processes that will try to equilibrate your leptons and thereby destroying your lepton asymmetry. What we find by explicit computation is that we can parameterize the different terms by these constant parameters that only depend on the parameters of the model, Cn, Cw, and Cs, times some z dependence. And here what's also important to notice, we have this exponential suppression for large z, which just reflects the fact that Olga has explained that at late times the temperature drops and the number density of the particles also drop. And so at some point these reactions, they freeze out because they become slower and slower until they eventually freeze out and nothing changes anymore. Now, what's convenient about this choice of masses is that since the Majorana-Fermion is your lightest dark particle, it is absolutely stable because it cannot decay into standard model particles, and it's therefore also a dark matter candidate. And we already have an equation to compute its abundance for late times, and we can do a scan of the different parameters. So here we are plotting the dark matter relic abundance for different values of this decay parameter Cn and for different values of the mass. And so it's clear that for larger decay parameters, we're producing a larger number density of dark matter particles. And so in order not to overproduce dark matter, we have to lower its masses to compensate for this larger number density. But we know also that we have a lower bound for the mass of the dark matter particle. Otherwise, we wouldn't get the same structure formation as the one that we observed today. And what we find is that the structure formation bound tells us that the dark matter particle has to be larger than a few keV, and this will give us an upper bound on this decay parameter so that we land within this region here where we're not overproducing dark matter, but still consistent with this bound. Now let's look at lepton asymmetry. I won't have time to go into the details of this plot, but essentially what we're doing is we fix the source parameter, we scan over all the remaining parameters, and we find certain regions where we produce the correct baryon asymmetry, which are given by is the area contained within this white line here. And of course, if we lower the source parameter, the regions, they tend to shrink until at some point there is no region anymore where we produce the correct baryon asymmetry. And with this, we find a lower bound for this decay parameter. Finally, coming back to neutrino masses, we can write the neutrino mass matrix in the following form, where we have here the Yukawa matrices, and we have this lambda matrix that is coming from the lepton the loop contribution that I've shown you before. So lambda has this approximated form here. And we also know that in the neutrino mass eigenbases, the mass matrix has to have this form. So after we have fixed all the other parameters, the Yukawa couplings and the masses in our model, the only thing that the only free parameter that we still have is this. Where is this? Okay. is this lambda 5, your scalar couplings. And what we can do is, I think this is not working anymore.
How can I use the back and forth here? Is that working? Okay. Disconnect it for a second. Give me a second.
So sorry about that. So resuming where we were, as I mentioned, once we fix the Yukawa couplings and the masses of our model, the only free parameter we still have is this scalar coupling lambda 5. And so we can, in a way, invert this relation to isolate lambda 5. And in this way, we can simply determine them from the other parameters in the following way. So now trying to wrap up everything that we have done so far. We have the decay parameter, which has this form here. And since we have this upper bound in them, we can make either the Yukawa couplings tiny or eta large in order to obtain, to be consistent with this upper bound, Cn smaller than 10 to the minus 3. For the decay asymmetry, as I've mentioned before, it is proportional to this term here, where we have a resonant enhancement due to the scalar masses. And so if the scalar masses are sufficiently close to each other, it's easy to obtain a source parameter larger than 10 to the minus 6. And finally, once we have set all other parameters, we can simply determine lambda 5 using this relation, and we are able to reproduce the neutrino masses that we observed today. So coming to our conclusion, what we have done in this work is we have explored this new mechanism for leptogenesis with the two Higgs scalars, Higgs scalar doublets, which to my knowledge had never been applied to a complete model. Using this model, we are able to explain neutrino masses, the baryon asymmetry of the universe, and dark matter with these two Higgs and a single Majorana fermion, which also to my knowledge hadn't been done before. And what is still left to do, we still need to understand certain aspects of the joint parameter region a little bit better. There is this other interesting region, so we assume that the Majorana fermion is lighter than the scalars, but in principle, it could be the other way around. And this is also a very interesting possibility that we are still investigating. And finally, there are some other phenomenological implications of this model that we still have to understand a bit better. So I thank you all for your attention, and I'm happy to take questions.
Yeah, but I'm sorry about the hiccup there. Yeah, we can maybe. So please ask question while I'm trying to fix the issue here. Actually, this is not working at the moment because it's going via this computer here.
Can you see the question?
Yeah, sure.
Yes. Okay. So my question is about the model, because in your matter scalar field and you have the neutrinos, and when you generate them. Dark matter mass at one loop or the right?
So the question was about the dark matter mass. No, the neutrino masses are generated at one loop. The dark matter masses are a parameter of your model. You have to input that.
And what about loop corrections to the dark matter mass through neutrino loops?
Let me think. Okay, we haven't considered that. See, in print. Yes, I think we haven't considered that. I would assume that this is a rather small correction, but yes, no, we haven't considered that. Okay.
What mass is the or no? Okay, I'll come back to you.
Yes, okay. Other question?
So you still require really small power couplings to make it work, right?
Depends. It depends. Yes, sorry. So the question was whether we still need very small Yukawa couplings for this. Where can I see my screen? Right? Can I go to full screen? Let's see.
Or how this, yeah. It's actually still on the other desktop here.
Okay. Right. So as I mentioned here, not necessarily if your scalar masses are high enough, you don't have to have very small Yukawa couplings. For instance, in our computation, we found something like of the order 10 to the minus 6 and minus 7, something like this. Yes. Yes. Okay. Slide. Kind of see the slide numbers. You tell me when to stop. This one. Yes.
Why do you consider the correction?
Okay, the question was why we didn't consider the vertex correction. Now, I'm not sure we have a vertex correction.
I think it's possible because in this kind of model, there is always two loops. There's an energy and the vertex.
Yes. Okay. So the question was that usually one has a wave function correction and a vertex correction. In this case, I don't think you get a vertex correction, right? Because you would have to couple this fermion propagator to another fermion propagator. You don't have a vertex that connects this, so I don't think you would get a vertex. Okay.
I have a way for that because maybe I can show you the
Let me see. Let me end there and then.
This is good for coffee talk.
Yes. Okay. We can talk about this later. Yes.
Quick final question. In that case,
Yes.
yeah. What is nonsense in case of super or super extension of standard model?
Okay, so the question is about supersymmetric models. I'm honestly not familiar with supersymmetric models, so I cannot answer that question. Sorry. Okay. Thank you.
Again, sorry about that.
No problem.
So I'm trying to switch back.